let's start our class. Today's topic is rank nullity. And for the fundamental matrices, we will further from the previous chapter. I forgot what we did until this class. So I summarize what we will do today is we will rank and nullity and the property of them. Actually, we can define it is from dimension of some image of operator, and nullity can be set as the dimension of solution set. The set of solution. For an operator T. So if we think about it, these objects will depend on the domain of the domain of the operator T. And so today we will focus on the meaning of domain. So the first theorem is the row space and the column space for a matrix A. Or matrix A have the same dimension. We will talk about the dimension, so we give some property of dimension. The same dimension. And give the proof. Before this class, in the last class, we proved one theorem, that is the independency of column space and the row space will not change from the elementary row operations. So that means it is okay to consider only the reduced row echelon form, because the reduced row echelon form will be given from the elementary row operation. If some A row echelon form will make some this stair shape matrix, and reduced case will say another is or 0 with some element. It was reduced to the row echelon form, and if we focus on the leading one, then we will count the number of leading one. It is same when you see the column vectors or row vectors. It has same leading ones. So the proof is simple. Since the elementary row operations do not change the linear independency, So that means do not change the dimension of row space and column space. And also, as I said, the number of leading one will be the dimension of column space and dimension of row space, and these are same, so the row space and column space has same dimension. I have the same dimension. And so now we define the rank and nullity. It's better to write the left side. It is not in the video. From this theorem, we can see that there is the common dimension of row and column space. Of matrix A, and which is called the rank of A, and which is denoted very simple. It is denoted rank of A, and sometimes it is simply right as this. And the definition of dimension is that the dimension of the null space was the space of solutions that of homogeneous linear system for the operator T. So the dimension of null space can be defined as the dimension of null space, and we will say it is the nullity of A, and we denoted it as nullity of A, or just we might write dimension N of A. N of A is the space of nullity. So let's see the example. On the example. We may already saw the example, maybe in my memory. 2, 4, 2, minus 7, minus 5, minus 9, 0, 2, 2, 2, 4, 0, 4, minus 4, 5, 1, 6, 4, and minus 3, 4, 1, 7. We will calculate the rank and nullity of A. This matrix is A. Then we already see that the row echelon of elementary row operations will not change the dimension of rank. So let's find the reduced form. Firstly, from adding from the second row by adding first row and -2 third row, we will remove the row second. I will write the first row 5 3, and I will calculate the first and second row to remove the third row, because if you add, maybe we did it. But we didn't give the rank and nullity, we just calculated. So, then let me just write the answer. By adding the first and second row, we will get the 0, another one, and 2 row vectors are linearly independent. If you make the reduced echelon form, then it will remain this term, because this block is linearly independent. So from this you can see that the dimension of row space is 2. That means the rank is 2, because we defined the rank is the dimension of row space or column space. It has same dimension. And the nullity case, if you calculate the nullity from here, then you will calculate the homogeneous equation from here. Common mean here, common mean is just the dimension of row space and the dimension of column space is same, so it has common dimension. New row and column. You mean in yeah. Independent column. That is it would be possible. It looks would be possible, but we are working in a good field, like we are working in a field. We are in complex, and in this field number system, if you calculate the dimension of row space and column space, they will have same dimension. Yeah. So some mathematical textbook might define the at least one, but linear algebra case, we usually the vector space will define it over a field, and on over a field it will make sense this theorem, and then this definition is well defined. I'm calculating to be back our class. And nullity of this nullity is the space of solution of this homogeneous linear system. And calculating this is same to calculate the homogeneous system here, and that means it has we already see that the second row and first row and second row are linearly independent. So if you make the reduce the row echelon form, you will have two leading ones, and another one would be three terms. And so the free value have four dimensions, so the nullity is four. And from here, you can see one surprising answer, that is, it has 1, 2, 3, 4, 5, 6 variables when you see a linear system, and if you calculate the rank and nullity, the sum of rank and nullity was 6, and it works in every situation, and this is called the dimension theorem. Of matrix. And sometimes it is called the fundamental theorem, the fundamental theorem of linear algebra. If A is a matrix, with n columns, that means in here case you have 6 columns, you calculate the number of variables if you see as a linear system. So then the theorem says the rank of A and the nullity of A is same to n. If you already calculate the rank of A, and if you know the number of variables or the number of columns, then you can get the nullity, although you do not calculate it. It is not inequality. It's really equal to n. So when you see a figure, if there is a vector space V and you have an operator on V, then it will it is not it is okay. Do not think only operator. I will just say linear transformation. Then the V will into the space of W in W as a double space, and in here some vector space will collapse by the linear transformation T, like just if you consider R3 to R3 a linear transformation, and if it map to like this 0, 1, 0, and the third one is 0, 0, 1, left 0 vector, then in this case the linear transformation will collect the third entries. Like this, it will collect some entries like this way, and the collapsing dimension will be a nullity because the row echelon form will not change the dimension at the dimension of rank row space. So something will go to 0 in V prime. For a vector V in a vector space V prime will go to 0, and if you calculate or elements like here element will be if send a vector W prime from V prime, then by adding another vectors in V large V prime, I will denote V bar. Then all elements in V will be denoted V prime plus V bar, and it will send the image of here. And so in this sense, we can divide the space V to a range space and the null space. The dimension theorem is saying that. So when I start this class, I said the domain, what we will deal with the domain of linear transformation. Actually, the proof is exactly same. So I will skip. I just mentioned that sketch of proof. It is the number of leading. When you calculate the row echelon form, the leading one variables and the number of free variables will be the number of columns or the number of the variables. So that's all. The proof is simple, but it's very strong theorem, because when you calculate, it means actually calculating the rank and calculating the number of columns is very easy. Usually the number of columns will be given, and by calculating the range is just calculating the dimension of image of the linear transformation. You can get the value of rank. And in this sense, you can get nullity as well, although you do not calculate it exactly. And the next theorem is let A be n times n matrix. Then the rank of A is same to the number of leading variables. Leading variables means the leading one. Variable in general solution of the homogeneous equation. As we calculate it, it will give the leading variables will give the rank, and similarly the free variables, nullity of A will be nullity of A. So it means the number of parameters in general solution of this homogeneous linear equation will be the nullity of A. because nullity, when we calculate the nullity, we counted the free numbers as the parameter. And I will write a remark that is about the fundamental space. It's our matrix. Just that this theorem sometimes called it the fundamental theorem or linear algebra, and the reason is in linear system or in vectors, when we deal with vector space, we always consider the 6 invariant vector space. There are 6 important vector space associated with a matrix M by M matrix A. From here we can get the vector space, the matrix A transpose, and it will give row space of A and column space of the A and null space of A. Similarly, we can calculate row space of A transpose and column space of A transpose and null space of A transpose. And as you can see, we already calculated the dimension of rows. The dimension of row space and column space is same, but actually the vector space is not same. It is isomorphic, but I will say just if you give in this example, if you calculate the row space, will be calculated these 2 rows, but the column space will spanned by the first column and second column. So the column vectors in R to the 2, R to the 4, and the row space, row vectors in R to the 6. So actually, it is isomorphic, but if you denote it like this form, then it's actually not the same space. So but when you consider the column space of A and row space of A transpose is exactly same, because the transpose is just changing the row and column. So in this sense, there are 4 vectors, exactly 4 vectors space for a matrix M by N matrix A, and these are called the fundamental spaces of a matrix A. And the dimension theorem also saying that the number of columns of A transpose will be M, because it is M times N, then A transpose will be the matrix N times N. So the number of columns will be M, and then this means the nullity will be calculated from n minus rank A transpose is same to here, and I will write it R. Then the nullity of A is n minus R, and when you consider it on the space A transpose, on a matrix A transpose, then the number of columns will be n, and it will give the nullity of n minus R. And it was a dimension, so that means the rank cannot over than n. So I think your question is from here. Since the dimension of row space or column space cannot be over than the number of m or n, so it will give I will remark one more. It will give the inequality rank of A is smaller than m or n, and n is the size of column or rows. And to say this, I just mentioned that the rank of A and the rank of A transpose is same. It is really true. A is any matrix, then the rank of A is same to the rank of A transpose. It is simple because the meaning of rank A is the dimension of row space of A, and it was same the column spaces of A transpose, and it was the rank of A transpose. So, as I said, we have only 4 important vector space for matrix A. Now, I just will define, but I will not explain in detail for this definition, because to talk about it, we need product exactly, but it is further class. So I will just mention the definition of orthogonal complement. W is a subspace of R to the n, then the set of all vectors in R to the n that these vectors are orthogonal to every vector of W, vector in W, is called the orthogonal complement. And it will denoted W perp, W to the perp. And actually, in here orthogonal means if some vectors in some vectors in R to the n, it cannot be expressed by linear combination of an elements in W. It will be called it orthogonal. So in here, what is better than I think. In this sense, when we see the vectors in outside of null space, and by adding the vectors in null space elements, we it is not a good explanation. When we calculate the rank and nullity, we saw that the row space and until so far we learned that rank is the space of row space and x equals 0 is the null space is the space of solution set which satisfies this linear system, and then if you consider the row vectors, it do we study dot product in maybe in a vector the previous section, previous chapter we learned dot products. Maybe in the last semester. Then when we calculate the linear system, if you write a1 to an and it is x1 to xn, then the first row will give a linear equation an xn equals 0. And it is the form of dot product with the row vector and with the column vector. So from the dot product is 0 means the two vectors are orthogonal. So if a vector in R to the n v, every element it is. If you calculate the dot product for every element in W and it would be 0, then it is the element of W perp. The solution set will be the orthogonal elements for the row space. Yep. Row A is the row defined as a row space of A, then its orthogonal space is actually same to the null space of A. There to mention that there are more theorem, but I will skip it because I think it is better to explain after we learn the orthogonality and inner product. And we have seen that the equivalence property for invertible matrix of A and I will skip from B to others. We have seen that the invertible matrix A is equivalent to the determinant is 0, or the reduced row echelon form will be identity matrix. We have seen these properties, and I will add some properties, some equivalent property more. The column vectors of A are linearly independent. And K is the row vector space. It is, if you consider a reduced row echelon form, then it makes sense because reduced row echelon form will be identity if A is a invertible matrix. The reduced row echelon form is identity, and identity matrix have all linearly independent column vectors and row vectors. So it makes sense, and L and M is the column vectors of A form a basis for R to the N, and the row vectors form a basis for R to the M. R to the N. We are considering the invertible matrix, and invertible matrix is square matrix, so it is the space of R to the N. It is also will be given from the reduced row echelon form identity. And the rank of A is N, means the reduced row echelon form is identity, and so it means rank N, and the dimension theorem is saying that the nullity of A is 0, because the sum is the number of we have to rank. It should be n minus r, but r is n, so the nullity is 0. And actually, as I mentioned like that, the row space is the orthogonal space of row space is nullity space, and if you believe it, then that gives the row space of A is R to the N, and the null space of A is zero vector space, because the null space is 0. The dimension of null space is 0, means it is zero vector space, and the orthogonal space is represented here. I will mention one more again. And the null space orthogonal space is row space. Because dot product has the symmetricity. When you calculate A1, X1, that 0 is same to X1, A1 is same. So the purpose space will the orthogonal space will be commute. The orthogonal space of row space is nullity, then the orthogonal space of null space is row space. So it is enough to calculate the null space of A is zero vector space, then the row space will be R to the n. Do you take a rest time?